FAN is a common tangent to the smaller circle ABCD and the larger circle ARZP. FP is a tangent to the smaller circle at C. The straight line ABR meets the larger circle at R. Right. So now they say prove that BC is parallel to RZ. So where is our BC and RZ? So let me just look at that. So we have this BC. We need to prove that it's parallel to RZ. Before we even solve this question, the point that they're trying to make us prove for is that we need to find a way to either prove that B1 is equal to R1 plus R2 or C2 is equal to the angle Z, right? Or just try to find some alternating angles in this way. But that's the main idea. So now what I see here is we have this A1 right here, which is equal to Z. This is because of the tan-chord theorem. So we have A1 being equal to Z. You can write this as RZA for good measure. Let me just write RZA for good measure. So RZA because of the tan-chord theorem. And then another thing is we see that there is a smaller circle inside the larger circle, and that also has the chord AB that subtends C2. So we can also say that A1, this angle A1, is equal to C2 because of the tan-chord theorem, because AB subtends C2. So we can also say that A1 is equal to BC. Actually, let me just say C2. A1 is equal to C2 again because of the tan-chord theorem. I'm not going to write it again. So A1 is equal to C2 because of the tan-chord theorem. So if A1 is equal to RZA and A1 is also equal to C2, this must mean that C2 is equal to RZA, right? So we proved that C2 is equal to this angle. Therefore, we can conclude that BC is parallel to RZ because of what? Because C2 is corresponding to RZA. So we can say BC is parallel to RZ because of corresponding angles. So let me just say corresponding angles like that. We've proved that BC is parallel to RZ like that. Right. Hence prove that BC is a tangent to circle ACP. So we just found that this angle is equal to this angle. This also means that this angle is equal to this whole angle, R1 plus R2. So now they say prove that BC is a tangent to circle ACP. Where is ACP? ACP is ACP. And this is our BC that we just proved that it's parallel to RZ. So if we are to prove that BC is a tangent to ACP, we need to find a way to make this angle equal to this angle because of tan-chord theorem. Because this will be a tangent, because BC will be a tangent, and AC will be the chord inside the circle. So we need to find a way to equate C2 to P. And it turns out there is a way for that. The way that we can use is we can see that the angle RZA is equal to the angle RPA because they are angles in the same segment, right? They are subtended by RA, by the common chord RA. So they're angles in the same segment, right? So we have angles in the same segment. So if Z or RZA is equal to RPA, this also means that C2 must be equal to RPA because C2 is equal to RZA. We proved that in the last question. So if C2 is equal to RPA, then we did prove that BC is actually a tangent to circle ACP. This means that we can therefore say BC is a tangent because of the converse of the tan-chord theorem. So converse of tan-chord, right? Because we proved it backwards or in reverse. So we found that these two angles are equal, and because it is an assumed circle, we therefore say it's a converse of a tangent theorem, just like that. So we did prove that BC is a tangent to circle ACP, just like that. So this is just your 3 marks. You don't need to think too much about it. Now, prove that triangle RZA is similar to triangle DPC. Let me erase this. So to solve these kinds of questions, I usually use one of the greatest tricks that I've been taught by one of the greatest maths teachers out there. So here's what the trick is. The trick is you first outline what triangles you are asked to prove for. So in this case, we are asked to prove that triangle RZA is similar to triangle DPC. Right. So what do I mean by outlining them? So the first way is you draw triangles that emulate each other in direction. So in other words, when you draw RZA, in this case, RZA, we went in an anti-clockwise direction, right? So this is your triangle RZA. If you chose a clockwise direction, for example, RZ being on the right-hand side and A being on the left-hand side, it also means that your DPC as well needs to follow the clockwise direction. So because we chose the anti-clockwise direction, so we also need to draw DPC in that way. So this means we'll start at D, we go down to the left because it's anti-clockwise, that will be your P, and then C, like that, right? So we now have these two triangles that we are trying to prove similarity for. So right, to prove similarity of two triangles, you either have to prove that all the angles are equal. For example, you need to prove that this R is equal to D, or this angle is equal to A, or P is equal to Z, right? Or you need to prove that all the sides of the two triangles are proportional. That's how you prove your similarity. So in this case, let's first get the things that we already know out of the way. So first of all, they're looking for these triangles. So they're looking for RZA. Apologies for that. And DPC. Where's your DPC? This is your DC, but you start with DP. Apologies for going to C. It should be DP. C, like that. So this is your first, this is your second, this is your third because it's DPC. This is your first because it's RZA. This is your second, this is your third, which means first we need to find a way to equate first and first, second and second, third and third. So now let's first get the things that we already know. We already know that this angle Z or RZA is equal to this angle, because we proved it in 11.2. So we now know that Z is equal to P in our triangles, in these contextual triangles. So we only need to find one more angle in the triangle that are equal so that we can conclude, right? Because the third angle of a triangle is always equal. It automatically becomes equal. So we just need to find just one angle that is equal, right? So what I see is, we see that the D2, this D2, is an exterior angle of the cyclic quad ABCD. I don't know if you see it because, you know, this diagram is now messy, but ABC is a cyclic quad and there's an exterior angle of D2. So this means that D2 must be equal to angle B. Let me just remove this. So I hope you guys can see. So this exterior angle D2 is equal to angle B1, right? Because it's an exterior angle of a cyclic quad. And because we just proved that BC is parallel to RZ, B1 must be equal to this angle. So this angle B1 is equal to R1 plus R2. This therefore ultimately means that R1 plus R2 should be equal to D2. Let me just write it down. So first we said D2, let me just use the white marker. So first we said D2 is equal to B1 because of an exterior angle of cyclic quad, right? So D2 is equal to B1. But we also did show that B1 should be equal to, let's call it ARZ, because they are corresponding angles. Since BC is parallel to RZ, right? So B1 is equal to ARZ. So if B1 is equal to ARZ and B1 is equal to D2, this ultimately means that D2 is equal to ARZ because they are both equal to B1. So the D and the R, we found that they are equal. So in our contextual triangles, we found that R is equal to D. So the third triangle will obviously be equal to each other. So if we found that D2 is equal to ARZ, now we can conclude that A, which in this case is just A2, so we can conclude that A2 is equal to C4. Why? Because it's a third angle of a triangle. We don't need to do anything crazy for that. So we found that two of them are equal, and then the third one will automatically be equal. So if that is true, we can therefore conclude that triangle RZA is similar to triangle DPC. But why did we conclude that? Because all angles are equal. So this is just triple A. So angle, angle, angle. So all angles are equal. So we prove that RZA is similar to triangle DPC because the angles of both triangles are equiangular. 11.4. Hence show that DC divided by CP times AC divided by AB is equal to 1. One thing I like about Euclidean questions is that they always follow each other, which means that if you solve something in 11.1 or 11.2, you will need to use it in 11.3 or maybe 11.4. And another trick that I have learned over the years through experience in solving most of these questions is that if you are told to, let's say, for example, hence show that this is equal to that, and the marks are greater than 4 marks, usually you'd have to prove similarity on another triangle. Because I said the things that we were using, or the things that we proved for, will be very important in this question, we still need those two triangles of ours. So we still need our RZA, and our DPC. So DPC like that. Now, what are we trying to prove? First, we write it down. We write that we are trying to prove DC divided by CP multiplied by AC divided by AB, right, is equal to 1. Now, let's see what we have. We have DC, and we know where DC is coming from. DC is coming from this side. And because this side is included, it also means RA must be included because these are proportional sides, because we just proved that they are similar. So if they are similar, it means DC is proportional to RA. And then we also have CP, which in this case it's this one, and it is proportional to AZ, right? So do we have AC? No, we don't have AC. Do we have AB? We also do not have AB. This is where I said we will try to prove similarity on another triangle because we don't know where to get AC and AB. And we also do not need to use RA and AZ because it's not needed in this question. So now we need a triangle that has both AC and AB, right? And when we look at our diagram, we see that a triangle that has both AB and AC is triangle ABC. So let me remove these blue lines. So a triangle that has both AC and AB is triangle ABC. Now look at this. So ABC, we need to try to find if ABC is similar to any of the triangles that we already have. And that one won't be a very hard thing to prove because ABC is inside RZA, the triangle that we already have. So this thing is already inside this triangle, this larger triangle of this. right? So this means that to prove similarity on that smaller triangle, it will be very easy, because what we can say is that this angle is a common angle, and this angle is equal to this angle because they are corresponding angles, and this one is also equal to this one because of corresponding angles. So, but let's write it down so you guys can see what I'm talking about. So first of all, we know that A2, because in triangle, let's just write in triangle because so that you can see what I'm talking about. So in triangles ABC and triangle ARZ, because I'm following that order. It's very important to follow the order. ARZ, A2 is equal to A2 because it's a common angle. And let's just say C2 is equal to RZA. You don't need to write the reason again because we've already proved this. So you can just say ellipses 10 point, is it 11? So ellipses 11.2. Was it 11.2? I think it's 11.1. So ellipses 11.1. So this means that you have already proved this in 11.1. You don't need to always write the reasons. So C2 is equal to RZA. This means that B1, we've already proved that B1 is equal to ARZ. Again, we proved this in 11.3. Was it 11.3? Yeah, it was 11.3. So this means that triangle ABC is similar to triangle ARZ because of the same reason. We found that all angles are equal. Now that we have ABC and ARZ, we can now enhance our triangles, right? So this means that we can come back and say in the triangles that we have, we now also have triangle ABC. But remember, I said order is very important. The way you write your triangles is very important. This means that, look at this. We want this order to be RZA. So to make this RZA, you would need to take this A and place it in front of Z. So this means it will be just RZA. This also means this A will move to be in front of C. So this will become BCA, so that we can write it in the same order that we wrote RZA and DPC. So now here we will have triangle BCA and in anti-clockwise direction. Now let's see what they are looking for. Let me just erase this proof. Right, so remember what they're looking for is DC divided by CP times AC divided by AB should be equal to 1. This is what we're trying to prove. So now DC is there and CP is also there. But we also found that there is another triangle that we need to look at. This means that this side is also included because it's proportional to all the other sides. So AB is proportional to DC is proportional to RA. So, but we do not want RA because it's not part of what we are trying to prove. So we discard RA. And then CP is wanted in our question, but AZ is not required, right? So it means that AC is the one that we should include. So we now have DC, CP, AC, which is this, and AB, which is also this. Now we can do fun stuff with what we have. So what we can do now is we can say DC divided by BA is equal to CP divided by AC. Right, we can do this because these triangles are similar. So because this triangle DCP is similar to triangle BCA, we are allowed to do this because these two triangles are similar, right? So if they are similar, we need to make these things look like DC divided by CP times AC divided by AB. So we already have DC at the top, which is where we wanted, and we already have BA, which is AB. It's just rearrangement. So we already have AB at the bottom. So we have DC and AB in the correct position. We need to put AC at the top because they want it at the top. and we also need to put CP at the bottom. So to put AC at the top, we can just cross multiply, which means multiplying this whole thing by AC. So this will now become DC multiplied by AC, all divided by, let's write it as AB because it's just BA. And then we'll be left with CP this side. So we also need a 1 this side. So to get 1, it's easy. You just divide everything by CP. This means you will divide this side by CP, and you also divide this side by CP. So this will become DC times AC divided by AB. This is the same as 1 divided by CP, and this is equal to 1, right? So we now have our CP at the bottom, and we have a 1 at the numerator. So we can just rearrange this because this means that AB is multiplying CP, DC, and AC are multiplying 1. So we can just rearrange this and say DC multiplied by AC, and we can take CP to come this side. So we can say all divided by CP multiplied by AB is equal to 1. So we actually proved that these are equal to 1. If you want, you can break this up and say DC divided by CP multiplied by AC divided by AB is equal to 1. And this is how you prove these kinds of questions.